Okay, so now we have the hinge, aka beam problem. Now, let's get right to it. It says a uniform 27 kilogram beam at an angle of 45 degrees with respect to the horizontal has a length of 21 meters. It is supported by a pin and a horizontal cable. What is the magnitude of the total force exerted by the pin on the beam? The acceleration due to gravity is 9.8 meters per second squared. So I make the drawing bigger so we can see it. This was very blurry. We can see it is, now we don't have a massless object like we did with the ladder. We have a 27 uniform kilogram beam. So the fact that it's uniform, it's going to help us with the center of mass. The length is 21 meters, and here we have 45 degrees as the angle with the horizontal, which this is the horizontal. So as usual, let's write down the given to know what we have. So given, let's try it again. So we have only one mass of 27 kilograms. We have length L of the beam, which is 21 meters. Theta is 45 degrees. And we have acceleration due to gravity, that is 9.8 meters per second squared. And then we have to find the force exerted by the pin. So let's call it FP for pin. Okay, this is a problem about torque. So we should do the free body diagram, which is what we're about to do. And so I'm just going to copy the shape, but let's go for blue to have consistency. So there it is, and yeah, let me just copy those lines so we can have a point of reference. There you go. And yeah, that's fine. So we have this, well, this beam is attached to a cable right here. So we have tension, correct? Here we have tension, and tension is going to the left. So let's add that vector. So we have tension. Let's go for red, as we like to do our vectors, our force vectors. This will be tension T. And we have now, since the ladder is uniform, the center of mass will be right at the middle, here. So we're going to have the weight of the ladder pointing down, and that will be weight equals mass times acceleration due to gravity. This is mg. And then we have the force by the pin, which is like this. That's what we're trying to find. So this is FP. There you go. Now, one thing I'd like to say about this one is in order to find the force of the pin, we have to find the y and x components, because look, it has a direction in 2 dimensions. Okay, so that's going to help us right now. And so let me do it right now. Let me move this FP over here. And I'm going to use green for those force vectors, just so that we can recognize them. Let's go for green. This will be the force of the pin along the y, FPY, and we'll have a force of the pin, there you go, along the x direction. And that's how we're going to label this one. Force pin x. All right. And let's identify the torques. For torques, I'm going to use black. So there's a torque here, right? Because if someone were to pull this cable, here's a pivot point. It'll move like this. So here's torque 1. Let's try the tau again. Man, I can never do the tau. Torque 1. And then we're going to have a torque due to the mass of the beam itself. So we're going to have torque 2. Okay. Now, let's account for the forces. So let's sum the forces. Okay. Now the system is in static equilibrium again. We should write it down. So let's write it down. The system is in static equilibrium. Whoops. I can't spell. There you go. So let's start with the summation of the forces. Let's start with the x. Forces acting along the x direction. It's not moving. This is equal to 0. And we have tension and the force of the pin along the x. So FPX minus tension. I can move the tension to the left, so I have that the force by the pin along the x equals T. Now let's sum the forces along the y is equal to 0. That'll be FPY minus the weight of the ladder, mg. Okay. So we can have that, or we can say that the FPY, force pin y, equals mg. Okay. Now let's account for the torques. The summation of the torques. Let's try it again. It's kind of funny. Now before we write down the torques, let's recall the general formula for torque, which is radial distance times force times the sine of theta. Okay? Now let me move it to this side. You'll see why. You'll see why. Okay. We have a torque here as we identified at the beginning of the problem. The length, so here's the force applied, here's the pivot point. So the radial distance from, or the distance from the pivot point is the length L of the beam. So then this will be 0 as it is not moving. So the length L times tension times the sine of theta minus. So we have the force, which is the weight of the ladder, but we need the distance from the pivot point to here. So we need the distance from the pivot to this point. And to show you how to get that, well, it's maybe you already saw it, we can use trig. So let me do this circle, kind of showing that I will. No circle. I'm just going to draw it. So let's go for, yeah, let's stick with blue. Let's draw the triangle. Whoops. There you go. It looks similar, somewhat, huh? And we'll complete the triangle. Now we know the entire length is L. The center of mass, due to the fact that this is a uniform beam, is right at the middle, right at the center. So this length would be length divided by 2, L divided by 2. If this whole thing is L, this is L divided by 2. So this is L divided by 2. This is theta. This is the opposite side, so this will be L divided by 2 times the sine of theta. And then the length that we want, this one over here, distance from the pivot to the weight vector, will be length divided by 2 times the cosine of theta. There you go. Let's move this here. And then the torque by itself. So now it's going to look like, I mean, they're related, but not directly. So now we have the length, which is L divided by 2 times the cosine of theta. And then we have the force, which is mass times acceleration due to gravity. And then notice, this is 90 degrees. So it maximizes the torque because the sine of 90 is 1. We'll leave it as is. I'm going to move this one to the left. That way we can have length divided by 2 times the cosine of theta times mg equals length times tension times the sine of theta. Let's rearrange this for consistency. Length times force times the cosine theta equals, actually I should have written force and then length. So this would be L divided by 2 mg, there you go, equals tension times length times sine of theta. Okay, now to find the magnitude of the force, this magnitude, I could use Pythagorean theorem, right, and get the square root of this squared plus this squared. But I have no way to know these forces unless I get tension and mg. So this is pretty simple. So truly I need to find tension to find the magnitude of the force of the pin along the x. So let's solve for tension. You know, it's pretty simple. So now let me just change this a little bit here. You'll see why. I'm just going to make this whole thing be divided by 2. I didn't change anything mathematically, just rewrote it in a different way. Oh, come on, I can't do parentheses today. Times the cosine of theta. Oh, come on. That is equal to tension length sine of theta. I'm going to divide cosine of theta. I think my pen needs battery, so give me just a second. This is a small unexpected break. Hopefully that'll work. Cosine of theta. Cosine of theta. This cancels, so sine over cosine was sine theta. Cosine over cosine theta is tangent of theta. So we have mass times acceleration due to gravity times length divided by 2 equals tension times length times the tangent of theta. Okay, we're trying to find tension, so we have, or we divide by length times the tangent of theta. This cancels. Let's do this on this side. And we have that our equation now reads tension equals mass times acceleration due to gravity times length divided by 2 divided by the length times the tangent of theta. And if you know how to do this operation, then it's very simple. You can make it into another fraction by dividing by 1. Then you can do the hamburger method that I taught you, right? So these and then these. When you do that, you'll have, so don't forget, cheese and patty go together, bun, go together. So it'll be MGL times 1, which is just MGL divided by 2L tangent theta. We get rid of the length, and tension will be the weight, that's mg, mass times acceleration due to gravity, divided by 2 times the tangent of theta. So let's see what that is. Here we go. So that is, what was the mass? 27? I think so. Yeah, 27 times 9.8. That's for acceleration due to gravity, divided by 2 times the tangent of theta, which is 45 degrees. Looks good. So the force along the y is, no, along the x, because it's tension, 132.3 newtons. So 132.3 newtons. What happened? Jesus. There you go. So now to find the magnitude of this force, again, it's Pythagorean theorem. It's just vectors. So then the magnitude, let's go for purple. The magnitude of the force will be, I'm going to do the square root at the end, okay? So don't get confused. Force x squared plus force py squared. And you take the square root of all this. That's how you get the magnitude. So we have that the force along the y is the same as the weight, which is the same as, so let's get that number real quick. I forgot to get it. That's super simple. So 27 times 9.8, 264.6 newtons. The force along the x, that is tension, which it was 132.3. So then the magnitude of the force will be 132.3 newtons squared plus 264.6 newtons squared. There's no way I'm going to do a straight line here, so I'm just going to take advantage of the OneNote tools. I will attempt to draw this one. Not that bad. So let's get that magnitude. Square root. Where's the square root? There you go. So we have 132.3 squared plus 264.6 squared, 295.8. Let's do it like that. 295.8. That is the force. 295.8 newtons. And that's how you find, better said, that's how you solve the beam problem.